Hi, everybody. So my name's Nick Stott. I work with Compose, and I'm a platform engineer. So we host a lot of databases right now. We host Mongo, Postgres, Redis, Elasticsearch, Rethink, RabbitMQ. So today, not as is written on the slide there, but we're launching a closed beta for Scylla. So if you'd like to email Scylla@compose.io, would be happy to let you have an account and try Scylla out. Let us know what you think of it on our platform. So I want to go into a bit of our backstory, so how we got where we are today. So the first phase of Compose, we were founded in 2009 as Mongo HQ. And we were the first MongoDB database as a service. We were in the Y Combinator class of 2011. And we've been using containers since our really early days. And this predated Docker and Rocket and all these tools that have sprung up recently. Without the container technology, we wouldn't be able to do what we're doing today. But it wasn't all lollipops and roses. We had some problems going on. We had really static deployments. And this is counter to what's going on with containers these days. Would spin up a host, would build a root file system with whatever Linux distribution we're using, and would copy that root file system 100 times, and then would wrap each one of those in a container, and would have all of these running on a host. And then as a customer comes in, we just allocate one of these running databases to the customer, and then move on. It was awkward, it was slow, and we were running the full Linux init system inside the container. So we had 101 copies of cron running. We had 101 copies of SSHD running. These are waste resources, and it didn't make a lot of sense for us. And everything was running on the public internet. Would open up high ports on these hosts, and then would NAT through a Linux bridge into the container. And so all the Mongo members, these were running and listening on the public internet. And it only worked for Mongo. We didn't have any other databases. We wanted more databases, but we didn't have that yet. And it sucked. It was hard for us. So we started on the next phase of our product. And where we wanted to go, we wanted more elastic deployments. So this is Compose Phase 2. With Compose Phase 2, we had more dynamic containers. As customers would come in, they'd connect to an orchestrator, and the orchestrator would spin up containers for them, and they'd deploy and destroy these containers on demand. And as this was happening, the orchestrator, this engine, we called it operator, this knew how to do a lot of things. It knew how to set up a Mongo replica set. It knew how a Mongo backup member was different than the other members. And it knew that how to add a Mongo user, which is good, but it's bad. In 3 different versions of Mongo, we had 3 different ways of adding users. And so over time, our orchestrator was getting really bloated. It was getting heavy. And everything was still on the public internet. This orchestrator, it was getting to be unmaintainable. There was so much going on there, lots of if, else's, conditional statements. If Mongo version A, then do this. If Mongo version B, then do this. It was really hard to work with. This was limiting us. And we were still running the entire operating system inside the container. And we wanted more. So how are we going to go beyond just Mongo? How are we going to host these other databases that we all like and what we use? Well, there's some things that needed to change. So at Compose, our containers, these databases need to be on a private network. Anything else just isn't going to be good enough. We want to be able to deploy and destroy these containers on demand. Our containers need to be really lightweight. And I want to take all that logic that's in this orchestrator and push it somewhere else. I don't know where it's going to go, but it's got to get out of this orchestrator. And our containers need to be lightweight, need to be very dynamic. As we're looking at all these different databases, so from the outside, all these databases look different. We've got different query languages. I'm going to query Scylla in a completely different way than I query Redis. I'm going to query Elasticsearch. It can use HTTP for Elasticsearch and use some sort of different line protocol for Mongo. Everything's different. We've got a different set of drivers that we're using to connect to these databases. They're all configured differently. The Scylla.yaml, entirely different from the redis.conf, which is entirely different from how Elasticsearch is configured. We need a different environment to run these things on. Elasticsearch and Cassandra, we've got all the way to the JVM behind these things. Something like Redis is a lot easier to run. I can have a really lightweight environment. These are all very different. So finding a common ground, it's very daunting. It's hard to find a way that these things are all similar. But there's good news here, too, because the more we looked at this problem, we were seeing that these databases needed more or less the same things happening. The databases needed to scale. There's something about a database that people just like to put their data there. And these things grow, and they grow over time. So we need to be able to scale up our databases. If there's a hardware failure, there needs to be some sort of failover. There needs to be a clustering involved in the database. All the databases need to back up and restore data. This is very important. And when I'm shutting down a database, it needs to quiesce nicely. And when I'm starting up a database, I need to make sure it's configured nicely. So this is important in the life cycle of these containers. I need these private networks. And I need to know when a database is doing well as opposed to when it's doing poorly. I need to know when a database is happy and when it needs help. So I don't know if you folks have ever heard of the 12 Factor app. And this is something that Heroku wrote, the 12 Factor Manifesto. And it was, I think, the first document that talked about how to host applications in the cloud. And it was with the rise of microservices. So what we wanted to do is we wrote a similar document. And this is the 12 factors of stateful apps. And so what do I mean by stateful? This is just something, the database, the application I'm running needs to remember something. It could be an application remembering its session store. It could be a database remembering its data. There's state here that has to be persistent. And so I've got listed here some of the apps some of the factors that we're talking about: configuration, deployments and processes, disposability. And I'm going to go into each of these and talk about a bit about it. So configuration, and this is something that's so I'm pretty lazy. We took this right from the 12 Factor app. But it makes a lot of sense for us. We want to take all the things that are unique about a database and put it in the environment. So things like the cluster name, things like the number of tokens that we're dealing with, things like an auth key, all the stuff that lives in that makes these databases different from one another. Let's put it in the environment. And this means that I can have one container image that spawns thousands of other containers, and the only thing that's different about them is the environment that we inject into them. But databases aren't going to run with this information only. I need configuration files. So we have a pre-start. We have a configure step in our spawning process. This lets us take this environment. We use templates, and we write this all out to disk inside the container. So for Scylla, we're creating a Scylla.yaml, and this has things like the cluster name, the seed addresses, these sorts of configuration options. Now, deployments and processes. A database isn't just one container. A database is a bunch of different moving pieces. So a usefully redundant database contains more than one moving piece. So let's decompose this idea of a database into all these different moving pieces. And these should all be running as stateful services inside their own containers. So for Scylla, we've got 3 data nodes, and we've got 3 proxy nodes. For Mongo, it's something a lot more complicated. For Mongo, we have 2 data members, an arbiter, a backup member, 3 config servers, 2 Mongo routers. Got this huge deployment for Mongo. Each of these are running in a separate container on the same private network. I want these containers to be disposable. I want these database containers to be entirely ephemeral. Pre-configuring these before we start is awful. We're not going to do that. I'm going to make it really easy to deploy and destroy these containers. But when I'm destroying a container, I don't want to destroy the data. And this is a pro tip. If anybody is running a database as a service, do not destroy people's data. You do not do well in that space if you do that. So what we do is we think about the database running in the container and the data as 2 different conceptual things. And these things have different life cycles. So the database container, I want to be able to stop it and start it. I might want to destroy it completely and build it up with a new image. And I don't want to touch the data when that happens. These things have different life cycles. And although they're different things for us, they're different concepts, they need to be in the same place. We're not going to be able to run a database with data that's mounted somewhere else, so on some sort of network-attached drive. Or we want to have really fast storage. We want to really fast SSDs that have this data really close to the container. And then we're going to bind mount pieces of that volume, that storage volume, right inside the container. And this data is it's persistent. It's got a different life cycle than the database. And I also don't want to have, I want to be able to access this data from the host. So if I'm running a heavy operation like a backup or a restore or some other mangling of the data, I don't want to run it inside our containers. Our containers are really resource constrained, and I don't want to overload them or impact the running database by doing this inside the container. So I want to be able to access this data on the host. So networks, private networks. Everything's got to be on its own private network. I want to have all my different moving pieces of a deployment on its own private network. And that network has to be different than this other customer's network. But our customers need to access this data as well. So we have this, these things we call portals. And these portals sit on the edge of this private network and proxy traffic in from the outside internet into this private network. So our data nodes, for Scylla, these 3 data nodes, these aren't going to expose any ports. Each one is going to get its traffic proxied through one of these portal containers. These portal containers are specialized. And this idea of specialized containers is very important for us. They're hardened, and they do expose a port. And these, similar to what we were doing before, we've got a high port on this portal host that's NATed through to the portal container that then proxies the traffic into the rest of the deployment. And I also want these portals to terminate SSL. Every database that we're dealing with handles SSL very differently. I don't want to have to solve this problem again and again every time we host a new database. So let's just solve it at the portal level. The portals are going to terminate the SSL and then proxy the traffic forward in the clear. So for Scylla, we've got these 3 data nodes, and it's matched one-to-one with a portal node. For Mongo, it was a bit different. We had the 2 Mongo routers forwarding to all this whole cluster of different containers. And when I'm starting and stopping these containers, I don't want the network identity to change. I don't want to have build a cluster of database nodes, and then every time I stop and start a database node, I don't want it to come up with a different IP address or a different host name. I want this stuff to be fixed. So every time I destroy or create a container, every time I stop and start it, it's got to have the same host name and the same IP address. That can't change. It's really traumatic to a cluster if we're bringing up nodes that all the time call themselves something different. But not only do they have to be static across restarts, I can't actually discover this stuff after the deployment has started, after these containers have been actualized. This auto-discovery is nice and convenient and works in some cases, but it doesn't work all the time for us. So I mentioned that Scylla have got 3 data nodes, 3 portals, and there's a one-to-one mapping. So what happens with Scylla is that the client does auto-discovery. So the client is going to connect to the portal, and the portal is going to proxy the traffic to a data node. And the data node is going to say, well, here's the answer, but you should also know about my peers, these other databases nodes that live here and here. And it sends that information back to the client. But if these data nodes just know about their private networking, the private addresses, then the client's going to get really confused, and it's not going to be able to connect to these other things. So we have these data nodes that advertise themselves as the addresses of the portal nodes. So when we create the data nodes, we have to know the addresses of the portal nodes. And when we create the portal nodes, we've got to know the addresses of the data nodes as well. And so it's a chicken-egg thing. We can't create one without knowing the other. So what we demand is that we need the identity of all the containers on this deployment to be known before we start instantiating any of them. We need to know this before we spin anything up at all. And databases need to scale. These things grow. And we want to be able to scale our containers vertically. So on a multi-tenant environment, if a database is growing and it needs more RAM, we want to be able to give it more RAM. We want to be able to give it more CPU or more disk, or whatever it needs. We want to scale these things vertically. And I don't want to have to shut down a data node just to add a few more resources. That's traumatic. It's highly impactful. It doesn't work very well for us. If there's some complex operation that's running on a data node, and I need to give it more CPU, but I have to stop the operation in order to do that, then I'm not getting anywhere. And Scylla is good at this. We can give it more resources. We can also scale these things horizontally. So there's going to come a point where I can't scale something up anymore, so let's start scaling it out. Let's start adding more database nodes. With Scylla, this is easy. There are a few other databases. This is pretty easy. I can do it with Elasticsearch. I can do it with Scylla. Postgres, Redis, MySQL. These are all hard to scale horizontally. I can add more follower nodes to a Postgres, and I can increase the read capacity of the cluster. But it's trickier to add more master nodes. It's trickier to add more leaders. There is master-to-master replication, but this is not easy for us to implement at scale. So these things are harder to scale horizontally like this. But as we're if we accept that growing horizontally is okay, then this is a good way for us to add other utilities to the deployment. So if I want to collect metrics from a specific database, if I want to know how many reads per second a Mongo is doing, then I can add a specialized container on the same private network, and this specialized container knows how to talk to Mongo. It knows everything about Mongo, and it's able to report that back. And we can send that back to a service, Datadog, or et cetera, or deliver it straight to our customers. Do the same thing with Scylla. Specialized Scylla container, added on the same private network. And this is able to query the database and then deliver that stuff somewhere else. And logs, let's collect logs the same way we're doing in the container ecosystem now anyway. Let's get all these databases log to standard out, and then we can use a similar set of tools that we're familiar with to collect all these logs, and we can ship them wherever we want. And really standardize that process. So the orchestration is it's a really hard thing. I said we had this operator, this orchestration engine, and all this code was being put in there. And this code knew everything about how to manage a database. It knew all about the different versions of Mongo that needed specific types of add user. And I wanted that out of there. I just want the orchestrator to be able to know how to create and destroy containers. That's all I want it to do. But where am I going to put all this stuff, all this logic? Let's put these in specialized database containers. Let's take that logic all out of the orchestrator and put it right into these containers. And let's run this. If we want to run add user, let's run that right inside that container with tools that know Mongo inside and out. But I'm not just going to act on one container. I want to act on the entire deployment. We call these recipes. And this is an ordered sequence of operations. And so let's say I want to back up a Postgres database. My orchestrator doesn't know how to back up. But it gets a request, and it says, back up this deployment. And it sends this off to the containers. And the first container says, well, I've been asked to back up. I'm currently a leader, and I don't want to do that right now. So request denied. And the recipe will go and continue on to the next container. And that container will say, well, yes, I'm a secondary, but I'm too far behind my leader, and I'm not in a healthy state, so I'm not going to back up right now. The third container is going to say, well, I'm a follower. I'm healthy. I'm close enough to my master. Yes, I'll do the backup. And then it sends that information back to the orchestrator. So all the orchestrator knows is that this operation was done by somebody. It doesn't care who. It doesn't know the details of the internal state of the database. And it doesn't really care. And that's a good thing. And so code base. I want these specialized images, these specialized containers that know how to work with a specific database. So let's make, for every database, let's have an image. And this image is the database binaries. And it's not just every database, every version of every database is going to be its own separate image. It's going to have the database binaries and the tools, the libraries that we need to run this. And each of these images can be used to spawn thousands of containers, and the containers only differ with their environment, the environment that we inject into them. But we need these tools. We need these tools to be able to manage these databases. So we need to be able to add Mongo users, which is an awful problem, believe it or not. So we have this tool chain, and this tool chain is versioned as well. We have a separate Mongo 3.2, Mongo 3.21, Scylla 1.0, Scylla 1.2, Scylla 1.3. And each of these overlays, we call them overlays, is kept in lockstep. The versions are matched with the image that we're using. And so Scylla released thrift support in 1.3. This is a great thing. And I want to be able to add that support to our databases. I don't want to have to worry about adding that with Scylla 1.0 or 1.2. It's only applicable for that one version of the database so far. So let's just have our tool chain support that. And when I'm updating these tool chains, there are bugs that get shipped sometimes, or we're adding features. And so I want to be able to update these overlays without restarting the database node. And so what we do is we overlay this tool chain onto the running containers. And then we can keep these up to date as we release bug fixes, as we add features. And so this is the 12 factors. We've managed to use these ideas to create a a really resilient and reliable system for multiple types of databases. We like to keep our orchestrator generic. We have the specialized tools that know how to handle individual databases. We've got the private networks and the slim images that make this happen. So I'd love for you guys to try out Scylla on our platform. If you email scylla@compose.io, there's a 1-month free trial, and try it out. Let us know how this is working for you. Would like to make this a really good experience, and we want to expose the power of this database, and we'd love to help you out with that. So thank you very much. I hope you enjoy the rest of the conference.